Good morning. So I think we are just about to start here. And let me start by saying that we really appreciate everybody coming here. There's nothing like starting your day with quality specifications and probability and all these fun things that'll just set you right. My name is John Yunt Pacheco, and I am a senior principal scientist at Bio-Rad Laboratories. And what we're going to be talking about today are how to react to new quality specifications. Now, the example that we're going to look at are changes in CLIA 2024. But the same principles apply to changing quality specifications across the board. So if you look at, for instance, the biological variation databases published by EFLM, you will see that they are changing on an ongoing basis. And how do you react to that? So that's what we're going to be talking about. We will end with a little discussion about how to use interlaboratory QC to predict performance on PT. So let me get started. So we've had some major changes in the quality specifications for the CLIA proficiency testing program. There's out of 101 performance specifications, there's only 21 that are the same. There's 29 that are new, and 51 of them have been updated, almost inevitably with more stringent requirements. This is the first major change that has taken place in the CLIA regulations, at least with respect to performance specifications, since things were initially published in 1992. But as I said earlier, the approach that you take to changing specifications works for any quality specification. So, just to give you a little bit of an idea, I've pulled here, and I know that these are probably pretty hard to read, but I pulled some data published by the CAP about here's what our current quality specifications are, and here's what the new CLIA criteria are. And so what you'll see is that in a lot of the cases, we've got more stringent specifications. So in this case, moving from a target value of plus or minus 3 standard deviations to an actual percentage presents a pretty significant change in the performance specifications. And that's probably the most usual scenario, but there are some, specifically like hemoglobin A1C, where actually they're using 2 different criteria. The CLIA criteria is actually at 8%, but then there is also a 6% specification that's used by CAP. And so you actually can be graded on both of those depending on what applies to you. But this is a pretty unusual scenario. What's a lot more common is this type of thing where, with this one, we do go from 10.7% to 10, and that's what you would expect through most of these specifications. Here's another example of going from 3 standard deviations down to 20%, and that's reflected throughout these quality specifications. So even though a lot of the analytes, they have been under CAP has been testing for them in their proficiency offerings, but what's changed is the federal limits for what's acceptable. So Quality specifications change over time, and what do you do when that happens? That's what we're going to address with our next two talks. Dr. Lauren Bachman is going to talk about how quality specifications impact a lab's reaction to an out-of-control event and troubleshooting. And then Dr. Nichols is going to talk to us about how it impacts your risk management. So let me just introduce our next two speakers. Dr. Bachman is a professor of pathology and co-director of clinical chemistry at Virginia Commonwealth University Medical Center. She is currently serving as a member of the College of American Pathology Accuracy-Based Programs Committee and is a member of the NIDDK IFCC Laboratory Working Group for Standardization of Albumin in Urine. Dr. Bachman is also a member of the Board of Directors for the Clinical and Laboratory Standards Institute, CLSI, and she serves on the CLSI expert panel on clinical chemistry and toxicology. Dr. Bachman's research and clinical interests include the development of laboratory practice guidelines, standardization of clinical laboratory assays, and quality assurance. She has provided numerous workshops, continuing education sessions, and seminars on quality assurance and other laboratory-related topics. And then we will have Dr. Nichols, who is a professor of pathology, microbiology and immunology, and medical director of clinical chemistry. I'm sorry, my slide advance here seems to be turned on. That's not me. Okay. And point of care testing at Vanderbilt University Medical Center in Nashville, Tennessee. Dr. Nichols received his BA in general biology pre-medicine from Vivello College, University of California at San Diego. He went on to complete a master's and doctorate in biochemistry from the University of Illinois, Urbana-Champaign. Jim was a fellow in the postdoctoral training program in clinical chemistry at Mayo Clinic, Rochester, Minnesota. He's board certified in both clinical chemistry and toxicological chemistry by the American Board of Clinical Chemistry. Dr. Nichols has spent several years as Associate Director of Clinical Chemistry, Director of Point of Care Testing, and an Associate Professor of Pathology at Johns Hopkins Medical Institutions. Jim later served as Medical Director of Clinical Chemistry for Baystate Health in Springfield, Massachusetts, and was a Professor of Pathology at Tufts University School of Medicine. Dr. Nichols is currently the President of the Clinical and Laboratory Standards Institute, and Dr. Nichols' research interests span evidence-based medicine, information management, and laboratory automation, point-of-care testing, and toxicology. So, Dr. Bachman, thank you.
All right, so thank you very much for that introduction, John, and thanks to Bio-Rad for inviting me. And it's early, so we'll try to make it through. So as John mentioned, my topic is evaluating the impact of an out-of-control event, especially in the context of changing quality specifications. So what is an out-of-control event? An out-of-control event is when the lab receives a QC failure to indicate an out-of-control condition, which is a problem with the measuring system that could be leading to erroneous reports, making it into the patient medical record. So these are my disclosures, and John mentioned some of them. I do have leadership positions in the CLSI, and I will be mentioning some CLSI documents. So these are the learning objectives for the presentation. We're going to identify the steps to recover from an out-of-control event, discuss how to evaluate the impact of an out-of-control control event on patient results, and we're going to use the concept of allowable total error to discuss this. And then we're going to outline approaches for preventative action if we happen to find that our lab's QC program is insufficient to identify an out-of-control condition, or if the quality specifications have changed, for example, in response to the new CLIA PT acceptability criteria. So the primary reference we'll use for the presentation is CLSI C24, Statistical Quality Control for Quantitative Measurement Procedures. So this document has a number of recommendations for designing an effective QC strategy, for selecting appropriate QC materials and QC frequency for your laboratory, for establishing QC target means and target standard deviations, for troubleshooting QC failures, and also how to recover from an out-of-control event. So this slide shows the normal process we perform in the laboratory. So the blue bars represent patient sample results. And then, so we're measuring patient sample results, and then with some frequency, we measure QC materials, so that's the black bar. If the QC material is within our acceptability criteria, then we are assured that the measuring system is performing as expected. However, if we receive a QC result that does not meet our acceptability criteria, then that could indicate that the measuring system is not performing as expected, or we have an out-of-control condition. So the document, C24 document, goes through a systematic step-by-step process on how to recover from this type of out-of-control event. And it's broken down into two phases. And so here I've shown phase one. The first step is to actually detect the analytical measurement system error via a QC alert. And this requires that the lab establish a QC program that is sensitive enough to detect when an out-of-control condition is present. The second step is to immediately stop reporting patient results into the medical record because, of course, we don't want to issue erroneous results that the physicians may be acting on. The third step is to investigate to determine the root cause of the problem. The root cause is the fundamental defect in the measurement system that is contributing to potentially erroneous results. We need to know the root cause in order to implement the appropriate corrective action to correct the problem, which is the last step of phase one. So here's an example from our lab. This is step one, detecting the analytical measurement system error via a QC alert. So here you see lipase results. These are Levy-Jennings charts for level 1 and level 2 lipase QC. And so you can see that historically the assay was in control, meeting our acceptability criteria. And then the lab received a 2.5S failure where 2 QC results exceeded 2.5 SDIs from the mean. So the lab receives the alert. So this is just an example of our QC program in action. The C24 document recommends that we set our target means and standard deviations with sufficient amounts of data. We need at least 10 days worth of QC data for a new lot to set the target mean. And the document recommends that we need several months worth of data to set the target SD. And this is because in that target SD, we want to incorporate as many sources of normal variation in the assay when it's performing as expected. So things like multiple calibration cycles, multiple maintenance cycles, multiple reagent wedges, for example. Of course, when you launch an assay, you're not going to have several months worth of data to set the SD. So you can set a preliminary standard deviation target and then revisit it after a couple of months that that assay is in production and refine the SD if needed. The document also recommends that QC multi-rules should be established to identify out-of-control conditions quickly. So our lab uses the 1.3S rule, the 2.5 within control rule, the 2.5S across control rule, an 1.5S rule. This is when 8 values exceed 1.5 standard deviations from the mean in a single control material. That will fire an alert, and it indicates development of a slow trend. And then also the range 4S rule, which is when the range between 2 consecutive QC points in a single control exceed 4 standard deviations from each other. That rule detects imprecision. So numerous publications have performed these kind of power analysis as seen in this slide that really show that the use of QC multi-rules really establish the best combination for detecting an out-of-control condition while minimizing the false alert rate. So the false alert rate is when the tech receives a QC failure, but there is no out-of-control condition present. And we want to minimize the false alert rate because we don't want tech spending precious labor resources chasing down problems that actually aren't real. Okay, so we've detected the analytical measurement system error by ensuring our QC program is sufficient to issue a QC alert when we have an out-of-control condition. We then want to immediately stop reporting patient results by turning off auto-verification in our LIS system if that's what we're using. If not, we can use a manual process. The next step is to investigate to determine the root cause of the problem. And I've listed the most common problems that we experience in my laboratory. So one very common problem is a problem with the QC material itself. So the vial has been taken in and out of the refrigerator too many times, it's been left on the bench too long, and it's degraded. Another common problem is a problem with the reagents. So we have a reagent wedge on board the instrument, and it has degraded even though it's still within its onboard stability claim. And so this happens with particular lots of reagent. This happens with, for whatever reason, one single wedge of reagent. This can happen with a particular shipment of reagents. So we have to look out for that. There could be a problem with the calibration, so maybe the lamp energy has declined some on our spectrophotometry instrument, and the instrument needs to be recalibrated, or the assay needs to be recalibrated. We could have an instrument problem, so common problems include etching in the sample probe or need to realign the sample probe, leaks in the pumping system or tubing, clogs in the waistline. We've had mixers break. The root cause of the problem could be due to inadequate maintenance, so we're not performing maintenance frequently or aggressively enough, or of course, improper procedures. So I think one thing that we found is really helpful for our technologists is to develop a systematic approach for root cause investigation, because techs, especially if they're new, can be overwhelmed. There's so many causes of QC failure, and we really wanted to develop a tool for them that they can start, they know where to start, they know the next step to perform for their investigation. Of course, this type of systematic approach will be unique to each measuring system, each laboratory, and maybe even each assay. So the first thing we have them do is repeat the QC. Now, this is not a repeat of the same vial of QC on the instrument. That is a useless task and not going to provide any information. We ask them to walk into the refrigerator, get a new vial of QC, place that on the instrument, test. If that passes, if the QC value is close to the target mean, then we can be relatively assured that the problem is just with the QC material itself and there is no measurement system problem. If the value is far from the target mean or fails, then we know that a problem with the measurement system itself is likely. So the next most common thing for our lab is that the reagent wedge on board the system has degraded. So we ask the techs to next replace the reagent wedge. If that causes a pass QC, great. If not, go ahead and recalibrate, because that's the next most common problem. Prepare a fresh calibrator, recalibrate. If QC passes, great. If not, go through a step-by-step troubleshooting process that we designed for each measurement system. If the tech cannot accomplish troubleshooting and fix the problem, then we call technical service. So that kind of step-by-step process is really helpful, especially for new people. Some additional tools for investigation of root cause include looking at the QC multi-rules, so which rule failed, does that give us any insight? Look at our Levy-Jennings chart, is this a shift or a drift, which would point us toward a road of further investigation. What about routine lab records? We have calibration records, reagent lot change records, maintenance logs. Maybe we put on a new reagent lot and suddenly we have a QC problem. Other lab records, like our 6-month linearity checks and our among instrument comparisons. So if we have a QC failure on one instrument and see, oh, the 2 other instruments, their QC is about to fail, we probably have a problem common to all those instruments, like the reagents. Another really useful tool is the peer group QC programs. So of course, Bio-Rad has one. This one happens to be Sysmex. And this is where the lab will submit its QC data in real time. and you get a real-time comparison to your peer group on your particular reagent lot. So this can be very useful for troubleshooting. So once we've identified the root cause, we now want to implement corrective action to correct the problem. So here I've shown that. For this lipase problem, we have put on a new reagent wedge. And when we put on a new reagent wedge for this assay, the manufacturer recommends recalibration, so that's what we did. And you can see that QC came back into the acceptable range. So most of the time we would say, great, we fixed the problem, we can recommence patient testing, which is true. But this is not the end of the recovery process. We still have the entirety of phase 2 to work through. This is where we need to evaluate the impact on previously reported patient results. So remember that we were reporting patient results. We had a QC failure. That means sometime before that QC failure, there was an out-of-control condition. Our measurement system had an error. So we could have reported already erroneous results into the record, and physicians could have acted on that. So once we evaluate the impact, if it's clinically significant, we need to take steps to mitigate patient harm, which involves contacting providers and issuing corrective reports, and then ultimately implement preventative action to prevent the problem from occurring in the first place. So here's our little graph of our QC results. So here we have a QC result failure, and the root cause was found to be a problem with the measurement system. Therefore, patient results before the time point of the QC failure could have been erroneous, and we need to go back and repeat those patient results from the time of the QC failure to the time of the last acceptable QC. This could be 3,000 results, depending on your lab's volume. So you may want to go back and repeat in subsections of time to find out where did the error occur, and then repeat all the patient samples after that. So how do we evaluate the impact on previously reported patient results? Because we don't want to issue corrected reports if we don't have to. Maybe the error is small, not clinically significant, and issuing many, many corrected reports is very disruptive to our environment, also a waste of tech resources. So we developed this little tool. It's basically just an Excel spreadsheet. And here, in the first column, the techs can put in their original result, and then they can enter the repeat result. The tool calculates the difference between the repeat and the original result and compares it against an allowable error. So for lipase here, I've set the allowable error to 10%. So if the difference exceeds 10%, then there's a little script that instructs the tech, yes, please issue a corrected report. If the error does not exceed the allowable error, the script says, no, do not issue a corrected report. So this can be used in the middle of the night. They don't have to call anybody, and it allows expedited review and automated decision-making for when a corrected report is needed. But the whole key to this, we'll take some questions at the end. Yes, and I will show you, I will show you the calculations used. Yes. Okay, so what is allowable total error? So it's an analytical quality goal that sets a limit for the combined effects of all sources of error, including analytical imprecision and bias, that are tolerable in a single measurement. And there are a number of CLSI guidelines that describe this concept. So there's the CLSI C24 document, the CLSI EP21 document, which is on total analytical error, but it does discuss allowable total error, and it's currently under revision, as well as a new document, CLSI EP46, which is under development, and that document is actually going to be dedicated to discussion of allowable total error. So how do we use allowable error limits? So we use them to establish quality specifications for numerous lab activities. They're super useful tools. So you can use allowable error to establish acceptability criteria for method validation, for designing your statistical QC program, which Dr. Nichols will talk about, for evaluation of the impact of an out-of-control condition like we've shown here, and also to determine acceptability criteria for proficiency testing, which is what CLIA has done. They have actually used allowable total error goals to set their new criteria for proficiency testing in combination with some data from state-of-the-art testing. So the European Federation of Clinical Chemistry and Lab Medicine in 2014 had a conference in Milan where they discussed how to establish allowable total error goals. And so allowable total error goals based on clinical outcomes is the preferred approach. So your error goal or error limit should not exceed the change of analyte concentration in disease or a change of analyte concentration required for therapy. And in fact, it should only represent a portion of that change. So you can get that data from professional practice guidelines and clinical trials data. You can also establish the allowable total error on biological variation data. So biological variation is the variation of an analyte when a patient's health status is stable. So that's the natural variation of an analyte, and it's different for different analytes. You can find this information in databases like the EFLM database and the Westgard database, and I will show you an example of this, because this is actually what CLIA used to establish the new PT acceptability criteria. You can also use state-of-the-art assay performance. This data can be obtained from the manufacturer's package insert, the scientific literature, and the lab zone validation data. And so please look forward to the EP46 document coming out. It's going to discuss each of these approaches thoroughly. Here's just an example. So this is the EFLM biological variation database. So I've given you the URL, the website link at the top. And what this database does is you can enter your analyte of choice. So here I've entered lipase, and the website returns biological variation studies that you can see under the reference section. And the ELFM has actually performed a meta-analysis of those studies and provides the within individual biological variation. This is the average variation of lipase within an individual. And also the between individual biological variation, which is the average variation of lipase between individuals whose health status is stable. So we can use this to calculate the allowable total error limits. So here, this database is nice because it has a little button at the top, analytical performance specifications. You can click that button and get the allowable error limits. It's using this equation shown. So you can see that the intra-individual variation and the combined intra and between individual variation estimates are there. And there's a few factors, 0.5 and 0.25 between those estimates. And that tells you the specification level that you want your allowable error to represent. So the website gives specifications of minimum, desirable, and optimal. And those factors in front of the intra-individual CV and between individual CV combined with intra-individual CV represent which specification you want. So here I've chosen desirable, and that is 50% of the intra-individual biological variation and 25% of the combined estimate. So your total allowable error cannot exceed those percentages. So if you want to move to the minimum specification, those factors get higher. If you want to move to the optimal specification, those factors get lower. So that's how that's calculated. So here we see for desirable, total error goal is 12.9%, and optimal is 6.4%. So I considered how lipase is used in my laboratory, the clinical utility, and decided to choose the midpoint, which is 10%. So that's how I figured out what to put in this tool to tell techs whether or not to issue corrected reports. Now, if I wanted to switch to the optimal of 6.4%, so here my quality specification or allowable error limit has changed, that will impact the number of corrected reports they need to issue for the same amount of difference when we repeat the QC after we've corrected the problem. So changing the allowable error limits changes the impact on the activity that you're applying it to. So as John stated, these are some examples of the CLIA allowable error aligned acceptability criteria. So they use this allowable error concept, incorporating biological variation and some data on state-of-the-art assay performance to come up with these goals. So the process for evaluating impact on patient care after PT failure is the same as you would do for evaluating impact on an out-of-control condition. You follow the same exact process. So the last step of the process for recovery from an out-of-control condition or PT failure is to implement preventative action. So frequently, part of the preventative action is to redesign your QC program to identify the out-of-control condition more quickly, or if you're not getting the appropriate alerts, to get the QC alert when you have an out-of-control condition. So to redesign the QC program, you can increase frequency of QC analysis. You can change the QC target mean or target standard deviations. You can add additional levels of QC materials. All of these will help improve the sensitivity of your QC program. And you can also use the allowable total error goals to establish your lab's QC approach. And Dr. Nichols is going to talk about the sigma metrics in context of allowable total error and how you can use this to adjust your QC rules. So in conclusion, we've discussed the steps to recover from an out-of-control event. This is a systematic process. Phase 1, detect the error, immediately stop patient testing, investigate and identify the root cause of the problem, implement corrective action. That's not the end of the process. You then move to phase 2, where you're evaluating the impact of the problem on patient results using allowable total error, mitigate patient harm by calling providers and issuing corrective reports, and finally, implementing preventative action to prevent the problem from reoccurring. So allowable total error is a very useful tool. It can be used to evaluate impact on patient results after an out-of-control event, or to make improvements to your QC program to detect error conditions more quickly and also respond to changing quality specifications. For example, if you find your lab is failing PT based on the new CLIA specifications. Okay, so that's the end of my presentation, and I think we will hold questions until the end. And now we have Dr. Nichols.
Well, thank you, and I thank everyone for getting up this early in the morning to listen to some math. So I'm going to talk about risk management, these changing CLIA specifications and what it really means in the laboratory for risk of failing your proficiency testing. So my disclosures, I am accepting an honoraria for this talk, and I am the CLSI president, so I will be mentioning EP 23 as part of this talk. So our objectives are to assess the quality of laboratory tests. How do we do that? I will define 6 sigma metrics and the impact of changes in the CLIA PT criteria and what that means for laboratories, to consider the risk of changing quality specifications and lab performance. So quality. Our laboratory assesses quality, and physicians rely on quality results from the laboratory. But how do we measure quality in the lab? We assess analytical performance of our instrumentation to meet medical needs. This is fitness for use. In other words, does the test actually meet the medical criteria to make a decision? And we assess that 2 ways. One is bias. That's systematic errors that lead to shifts in performance from one point in time forward. Could be a problem with calibration, standards, reagents, your blanks, your controls. We also assess imprecision, repeatability. If we test a sample multiple times, we all know we're going to get different results. So what is the spread of those results? And that's imprecision. So we can estimate test performance by combining bias and imprecision to calculate a sigma metric based on total allowable error limits. This combines both bias and our total allowable or total analytical error, bias and systematic errors. So bias is our systematic error, we can see here, and our random error, which is the spread of data. In terms of combining this, this is our total analytical error, which combines bias and 2 standard deviations. Our limits on this are in red bars. So this is our total allowable error. That is the medical criteria for determining quality. We want our analytical performance within that total allowable error limits. And there's where you can see our bias, our random error, and within the red limits. So Six Sigma is an assessment of both bias and imprecision. And we calculate that from our total allowable error. We subtract bias and divide by our imprecision. And state of the art is really Six Sigma. That is factory quality performance. That is less than 3.4 errors per million tests. So world-class quality is what we desire for all of our tests. When we think about bias, we think about imprecision and total allowable error, it sets us up for a quality budget. In other words, if we have a total allowable error of 10%, we can then assess our bias and imprecision in analytical performance within that allowable budget, that 10%. Let's take a look at how this impacts sigma metrics. So here's our sigma calculation. Remember, it's total allowable error minus bias divided by the coefficient of variation. If we have an analyte concentration, our control at 3, assay precision or imprecision is 2.2%. Our bias of 6.7 within a total allowable error limit of 10, we calculate a sigma metric of 1.5. If we have better precision, 1%, that raises our sigma metric up to 3.3. If, however, we lower our bias from 6.7 down to 2.7, we also raise that sigma metric. So you can see how this changes based on that allowable error budget, our assessment of our performance. You've seen the biological variability databases. This one came from RICO's publication, and they provide an estimate of desirable specifications for imprecision, bias, and total error limits for your analytical performance for different analytes. Using these metrics, we can assess the performance of our analyzers in our laboratory. We moved from one manufacturer to a new manufacturer in 2012. So after bringing that analyzer up in 2013, we assessed 1 year's of performance in 2014, October 2014, using total allowable error limits of CLIA compared to more stringent allowable error limits of RICO's publication and the Royal College of Physicians in Australia. So 3 different performance specifications. And we color-coded this at 3 different levels of quality control for different chemistry analytes. You can see albumin, alkaline phosphatase, ALT, and so forth. Optimum performance was green. That is greater than 6 sigma. Good performance was in yellow, and poor performance was in red. So just looking at color coding these, you can see albumin at the very top. If we use very wide limits, CLIA, we're assessing this as either optimum to good performance, versus if we use tighter stringency, the RICO's publication, we're poor performance. So, sigma metrics, we compared 2014 to 2016, and we said, okay, operators now know the instrumentation better. Are we going to get better performance? Is it dependent on the operator, these automated equipment? And what we see is really sigma metrics are fairly stable over time. The biggest difference is your total allowable error limit. If you have tighter limits, you're going to get an assessment that is poorer performance. Sigma does vary, and you see it varying from different concentrations. So at lower concentrations or higher concentrations, you may have different biases, different imprecision, and that changes your sigma metrics. Sigma also varies by analyzer. We had 5 chemistry analyzers, and so we assessed sigma metrics for each of those individually, combined them to get a mean, and that's what you're seeing, is the mean, and in parentheses, the range that we saw of sigma based on the variety of different instrumentation that we had. So based on this, we could predict a quality control strategy, but if we do it individually by each different analyzer, we're going to come up with different quality control strategies because the sigma metrics are different. So I would recommend, really, if you have a group of analyzers, take the more stringent approach, use the lowest sigma to define your quality control strategy. This gives us operation specifications if we think about sigma metrics. Here we're plotting on the x-axis allowable imprecision as a percent against inaccuracy on the y-axis. And you can see the different lines of performance for defining different quality control strategies, whether it's 1.2S, 1.2.5S, 1.3S. Basically, how you read these, if you're down close to 0% accuracy, percent imprecision, you're on solid ground. You're greater than 6 sigma. That's your green area on this chart. However, if you're less than 3 sigma, you have a wide inaccuracy bias, wide imprecision. You're up in the deep water, which is the dark blue. And so if you actually assess this on 2 different analyzers, these are Abbott analyzers, C16000 versus a C8000. These are Architect analyzers. You can see a line of 2 sigma performance going straight down the chart. And you can plot where the sigma metrics are. And you can see most of them are down in the solid ground, the green area. But we do have a few that are sort of in that in-between. Magnesium, CO2, direct LDL, sodium, chloride. These are sort of in that in-between area. These are the ones, these analytes, that we want to have a QC strategy where we pull in more levels of QC, maybe more frequent QC levels. Maybe we use tighter rules. Instead of using 1.2S rule, we go a little bit tighter, maybe instead of 1.3S, a 1.2S. You can see the difference between C16000 at the top versus C8000 at the bottom. Magnesium pops up again in sort of that in-between. CO2, urea. So differences between analytical performance based on different analyzers, even from the same manufacturer. So some of the sort of 6 sigma QC rules of thumb. If you're greater than 6 sigma, you can use fewer QC, use 2 levels of QC which meet the CLIA regulations, and wide limits, maybe 3, 3.5S, to prevent false alerts and troubleshooting, spending a lot of time troubleshooting in the lab. If you're at the bottom, less than 3 sigma, you want to use maximum QC that you can afford in the laboratory. Maximize your preventative maintenance, your function checks, deploy your most trained and skilled employees. So, we see these changes, and you heard John talk about the new analytes are added for PT testing, as well as more stringent limits. What does this mean? It means if you keep the same QC strategy, you're going to risk performance issues on PT, risk failing. So the impact of CLIA changes. Let's consider 2 different tests. Alkaline phosphatase. The old total allowable error limit of 30% now is tighter 20%. So if we have a QC mean of 33.45, our peer group is running around 33.62, that calculates a bias of about 0.5%. Our CV, or imprecision with this control at this level, is 4.5%. So let's plug this into that sigma equation. We calculate world-class performance at 30% total allowable error, 6.6 sigma. However, our tighter performance now, lowering that total allowable error to 20%, we're now estimating our performance as marginal. Same with glucose. If we have a glucose right at the cutoff for diabetes diagnosis, 123, our peer is reading 124.45, gives us a bias of about 0.68%. If that imprecision is around 1.8%, and we take an old total allowable error limit of 10, we're estimating our performance is pretty good. It's 5.2. However, the new total allowable error limit of 8% brings us into marginal performance. So we need to reassess what is our risk of failing proficiency testing based on these new CLIA changes. And I will say it's somewhat confusing. This is the new CAP checklist. This is going to be coming out later in October, November. And they give two different criteria for performance for hemoglobin A1C. If you were judging against your peer group, which is your methodology, you can use the CLIA limit of 8. But the NGSP program, National Glycohemoglobin Standardization Program, is an accuracy target-based program, and they use 6%. So again, you're seeing changes in specifications, and that's going to risk failure if you don't estimate what's going to happen or the impact on your laboratory. There are resources to help you assess this risk, and I would recommend looking at EP23. There are new guidance. This was just published a year ago in the fall, new examples. So that will help you in terms of assessing your risk. Let's use an example of this. Molecular point of care testing. We implemented molecular point of care during the pandemic for COVID respiratory viruses, flu, for instance. The manufacturer recommends use of positive and negative QC to validate new reagent lots. In accordance with local, state, federal, or accreditation organization requirements, additional control runs may be performed. That's straight out of the instructions for use, the manufacturer recommendations. But what about environmental contamination? We are putting a molecular device out there in the emergency room, and it is being run by nursing staff, by anyone under the sun who basically is picking up a sample. Are they going to carefully transfer liquid from the swab and the viral transport media into the cartridge? Are they going to get it all over the place? So, yes, if you get small amounts of DNA or RNA on countertops and you go through a PCR reaction where you amplify that many million-fold, very small amounts of contamination are risking a false positive. So we actually said, the package insert says, due to the high sensitivity of the assays, contamination of the work area with previous positive samples may cause false positive results. Handle samples according to standard laboratory practices. These are not laboratorians. These are clinicians out there in the field that are taking time out from seeing a patient to actually run a test. They want to get back to their patient. They're going to rush through this process. So clean instruments surrounding surfaces according to instructions provided in the cleaning section. Good laboratory practices and careful adherence to procedures specified in the instructions for use document are necessary. Wear gloves. Use laboratory coats. Eye protection when handling samples and reagents. Gloves must be changed between handling samples. Reagent tube. control kit to avoid contamination. So we took this as this is pretty high risk, that we could get false positives out there. So what we implemented was an environmental control. Outside of the recommendations of just test every new lot that you get, we're going to now test every operator's technique. So we want them, when we initially put that out there, to run quality control at least once a week during the initial months that we implemented this to make sure we were getting positive and negative from every operator. They knew how to run the test. And in addition, we put in environmental control, implemented basically taking viral transport media, taking a blank swab, and swabbing after we wetted that swab, swabbing the surfaces of the counters, the door handle of the room they were using, the keyboard of the instrument itself, the lid. And if we got a positive, we knew they were contaminating the environment. Our recommendations in the policy were to change gloves between samples, only handle one sample at a time, clean all of the surfaces after each sample, just to ensure that they weren't getting carryover. Lo and behold, things worked very well with this. This was our risk management table, and you can see in yellow the risk of contamination, and we implemented those environmental controls, despite the fact that the manufacturer didn't have recommendations like this. That was something additional that, as an institution, we implemented. So we conducted a risk assessment. Our quality control plan was additional quality controls, this environmental control. After we implemented that, we assessed how well is this really working. And in fact, in our clinics, the clinic staff, outpatient clinics, walk-in clinics, we didn't see any environmental controls. They were following the policy in that. Where we ran into problems was in our emergency room. They were rushing things. They basically, multiple times, we popped up 3 times in the first couple of months of monitoring. We popped up with false positives. So that told us something's happening with their technique in that particular site, that we needed to go back and have more education, look at them a little bit more stringency. So think about the change in your total allowable error. Think about how that's going to impact your proficiency testing, and monitor your failures, your frequency of your failures, to think about, do I need to put additional controls, additional frequency of my controls into effect? So in conclusion, the changing CLIA PT total allowable error limits are going to affect your PT performance. You should reassess your risk of failing PT. You need to change your QC ranges. Maybe you need to tighten the QC ranges. Need to add additional QC or alter the frequency, or look at your medical tolerance and the needs of the clinicians and patients. CLSI EP23 provides a resource for assessing a laboratory's risk in a world of changing quality specifications. I'm going to turn this back over to John. I want to thank you for your attention, and I will apologize. I do have an award I'm getting today, so I have to bow out at about 8:15. But if you have additional questions, you can always contact me by email, and I'll get back with you. Thank you.
Thank you, Jim. Okay, so what I'd like to talk to you about is how can we predict what your performance might be on a proficiency test? And we're going to use the CLIA 2024 specifications in this example. And what we're going to use to predict our performance is an interlaboratory peer comparison program. So, we'll talk first a little bit about the structure of the CLIA program, because that's important when we are considering how to predict its performance. And then we'll go into why is it even valid to consider doing this with your peer comparison program, And we're going to use then our pure statistics to compute several different probabilities that relate to PT performance. We'll end with a consideration of using risk contour plots and talk about the limitations of this approach. So the CLIA 2024 PT program consists of 3 events a year, and each event has 5 unknown samples. The PT samples are supposed to be treated exactly like you would treat a patient specimen. So for instance, if you have 4 different instruments that are testing a single analyte, you don't test it on all 4 instruments, the PT sample, unless that's what you're doing with patients. So you treat the PT sample exactly like a patient, and then it's scored according to the performance specification. You can, if you have 1 sample out of the 5 that is outside of the performance specification, that's still a pass. But if you have more than 1 that are outside of those specifications, that's a fail. If you have 2 out of 3 consecutive PT events that fail, then the lab is sanctioned for that analyte, and there has to be remedial action taken. So, if that's our structure, how does this work? Well, the most common PT performance criteria that you see in CLIA and in several other programs around the world is this idea that you've got a target and you have a width around the target. Now that target is derived from all the participants in the proficiency test, and it's the mean of their results, which is, of course, very similar to what we're doing in peer comparison. And the target, a lot of times it may be expressed as just a percentage, but a lot of times there is also an absolute concentration, and so you take whichever is largest. So in this example for ALT, the target is plus or minus 15% or 6 U per L, whichever is greatest. So if for targets that are less than 40, the criteria is going to be plus or minus 6. And if it's, then you can kind of see from my example here, the target's 55, you can see the range is 46 to 63. And if it was lower at 35, then it's 29 to 40. So that's just in general how the quality specifications work. And when we think about that, this is very similar to what we're doing with interlaboratory peer comparison, where we're collecting data from many labs that are using the same lot number of QC and the same test method, and we're developing peer statistics, including the peer mean. That's the most critical thing, which would be analogous to the target in a PT performance program. The other 2 relevant statistics that we need are the lab mean and the lab standard deviation. So if we've got a peer mean, a lab mean, and a lab SD, well then we can apply the PT performance criteria to determine what's our likelihood of producing results that would fail the CLIA 2024 PT specifications. So here's an example. You can see the peer mean and the limits that are computed around it, and then I'm showing the distribution of the measurement error on these results, and there's 2 critical factors that Dr. Nichols was talking about earlier. You have bias and imprecision. And so here you can see that with that combination of bias in this example, you can see that the lab mean is shifted lower then the peer mean, and you can see the dispersion of the results. And so in this case, that portion that's in red would be, that's the probability of producing a result that is outside of the quality specification. And that's the root thing that we want to compute when we're trying to understand what does our performance look like with respect to the quality specifications. So, if we've got a lab mean and an SD and a peer mean, well, there's 4 risks that we can compute. The first is, what's the risk of producing a result outside of the PT criteria? Now, that would be, in this illustration, what's highlighted in red. So what's my probability of producing a result that is on either side of the limits? Then we also want to know, if we want to evaluate how does this relate to the actual program itself, well, we want to be able to compute what's the risk of having a single sample, 1 of 5, failing the PT criteria. What is the risk of having more than 1, which would mean you would fail the event? And then finally, what's the risk of failing 2 out of 3 consecutive PT events? So that's what we're going to look at here. Originally, I was thinking, well, we can go into all of these nice probability calculations, but it's early in the morning and nobody wants to look at integrals. So we're going to use a little bit of a different approach, but this gives you an idea of kind of how this works. So the inputs into this are the lab mean and SD and the peer mean. I'm looking at 2 different levels. And then you can see the risks that are computed for each one of these levels. So we'll start off just looking at level 1. And what I'm going to do is use a probability calculator. So in these examples, rather than inflicting the probability statistics on you, there are calculators that are freely available that will take care of all the math, okay? So this is actually, you can see the URL. This is from a website called the Omni Calculator, and these folks have assembled a very impressive set of calculators for everything under the sun. There's literally hundreds of them. And in this case, what we want to take a look at is using the probability calculator for the normal distribution. Now that's how we're modeling what this looks like. And it's kind of hard to see this, but you basically, it's asking for what is the mean, the SD, and what is the probability limit that you're trying to compute. So in this case, the lab mean is 27, the SD is 1.8, and I want to take a look at what is my probability of, if my mean is 27, my standard deviation is 1.8, what's my probability of producing results that are going to be outside of the limits? So the limits here are computing based on the peer performance, the peer mean, and the PT specification. So in this case, because the lab is biased low, 27 versus 30, we look at putting in what's my probability of producing a result that is less than 24. And this is using the normal distribution calculator. And when you do that, it tells you what the probability is of producing that. Now, in this case, it's right at, if I look at it as a percent, it's about 4.8%. If I go back to my little example here, you can see that 4.8% is what we're looking at for the risk of producing a result outside the CLIA limits. Now, that's on one side. So if we go back to this distribution here, so we just computed what's on the left side. Now, we also have the possibility of producing results that are outside on the right. Now, as you can see, that probability tail looks really small there, and this is just in my little illustration. It actually is very small, so you can do exactly the same thing that I did here, except now looking at the other side of saying, well, what's my probability of producing a result that's outside on the high end? And it basically turns out to be very close to 0. So we don't really need to consider that. But that just gives you an idea of how you can use your peer statistics and your peer program to predict what your probability of producing results that fall outside of the PT limits. Now, if we start with that, so that's my probability of producing a result that's outside the limits. But what I really am interested in is how does that impact my performance in PT? Well, what we want to consider is what's my probability of failing a single sample? And let's start with that. So it turns out that there's another kind of calculator that we can use. Now what we're looking at is not just what's the probability of producing results that are outside, of one result being outside. What I want to look at is what's my probability of producing, if I test 5 samples, what's my probability that one of those is going to be out? And so we can use binomial statistics to compute this, and it's another very similar scenario, except now we're using a binomial distribution calculator. And if I go in, and again, it's hard to actually see the inputs in the calculator itself, but you put in that we've got 5 events, and what's my probability of failing a single event, or actually, in this case, what we're looking at is we want the probability of exactly one success, and the success that we're talking about here is actually having a result that is outside the limits. That's the definition of success in this case. It's a little, it may be a little bit confusing because we're talking about successes, but the success that we're talking about here is identifying a failure of one result. And when you do that, it comes out with 19.7%. And if you just sort of think about it, well, okay, if my probability of producing a single result that's outside the limits is close to 5, if I'm doing 5, it kind of makes sense that intuitively it's going to be somewhere around 20. Okay. So you can also then look at using the same type of scenario, we can go in and compute what's our probability of failing more than one. And so more than one failure is going to result in a failure for the event. And that's simply, all you have to do is change one of the inputs and say that I'm looking for something greater than 2 or greater, and it turns out that that is a much lower probability of 2.1%. So I can do exactly the same thing. So that just allowed me to compute what's the probability of failing a PT event. So I can use that in the same way to now look at what's my probability of failing 2 events, 2 out of 3. And so I go in and say I'm looking at 3 events, and I want to compute what's my probability of having 2 successes, which would be 2 failures, and it comes out to be quite low, 0.1%. So, one of the questions then that you might ask is, okay, I've got this risk of producing results that are going to be outside the quality specifications. What do I do about that? Or how would I know what the impact is of improving my imprecision or improving my bias? Because imprecision and bias are what drive the results that are going to be outside of the quality specification. Well, one way to do this is to compute a risk contour. And so basically, I'm going to look at a whole bunch of combinations of means and SDs, and then identify which means and SD combinations have a given risk. Thanks, Dr. Nichols. So, in this case, we're going to use the ALT level 2. The lab mean is 46, the lab SD is 3, and the pure mean is 50. So this plot is going to be centered on the pure mean. And you end up with this set of, let me see it. You end up with this set of contours. And so what you can see is that, so the dot is the lab mean and the intersection of the lab mean and the lab SD. And you can see that in this case, the risk of PT event failure is 11.5%. So you can see it's positioned, the dot is positioned just a little bit above the risk contour for 10%. So then the question is, well, what would happen if I was able to improve my, of course, if you reduce your imprecision, what's that going to do? That's going to pull the dot down. And you can see that if you go down not by very much, it can have a major impact. The other thing is true that if I just went from 46 to 47, so I reduce my bias, that cuts the risk by more than half. So this kind of analysis makes it easy to sort of see what can we focus on to hopefully have an impact on this, and what does that impact look like? Now, of course, none of these things are necessarily easy to achieve. It's not like you can just say, oh gosh, I just need to turn my CV knob down and everything will be better. But this at least gives you an idea of what the impact of having a difference in your imprecision or bias make. So, this gives you an idea of what your lab's performance looks like with respect to the CLIA 2024 proficiency testing specifications. But we also need to keep in mind that there are limitations. The first limitation is that most labs are not running 5 levels of QC. Most labs are running 2, maybe 3. Under a certain, there may be some analytes where you're doing a little more, but the prediction here is based on you can only use the concentrations that are present in your control materials to do this. And so if there is a significant difference in your bias or in your imprecision at a different concentration level, well, that may not be predictable just using your pure QC, because you are not generating results that are comparable. Now, hopefully, you're going to have a test method that's linear over the reportable range, but we all know that most of our analytes don't have a constant CV. The general tendency is that CVs are imprecision, grows worse as a concentration at the lower end and improves at the higher end. And so if it's difficult to then use your QC material and the interlaboratory comparison program to predict performance when there may be a significant difference particularly on the imprecision side of this. One way around this is if you're using a linearity program that provides pure statistics across the reportable range, then you can do exactly the same thing. And so if there is a concern, that would be a way to address that, because generally if you're using a linearity program that also has a built-in peer comparison, it allows you to do the same type of analysis. So, in conclusion, yes, we can use our interlaboratory peer comparison programs like Unity to predict our performance. In this case, we've taken a look at what we felt were 4 significant risks. You can use this very same approach for other PT programs, like for instance the RCPA PT scheme. As long as you've got quality specifications that are in this general format of plus or minus 1%, or maybe with various absolute concentrations, the same type of analysis works. And the main thing that you look at is you use the peer mean to set what the performance limits are, and then you can use your lab mean and your lab SD to see what's the distribution, the predicted distribution of your results in the context of those specifications. And if we use something like risk contours, it really helps for trying to understand how you might be able to improve the circumstances. And then finally, as I said, while this will give you information about your performance, there's not a guarantee, because you're not really modeling things exactly the same way that you would be with an actual program that's using 5 samples. And with that concludes our talks. Dr. Bachman, if you can come join me up here.
Q&A from the audience?
Hi, George Simbrowski. I'll be on topic and short. Lori, so good, like 10 stars, so perfect.
Thank you.
You've brought me into the new century. With the stuff that we get from Europe, they run it on the best analyzers to get these allowable errors. Plus, they get patients who don't represent American patients. They represent svelte Italian and Greek and Turkish women. So the biologic variation is stupid sometimes, and it's true, okay? So, but another problem is urea nitrogen specification. For an outpatient, they can drink all the water they want. In the hospital, they don't drink water. So the specification, if you're using the UN for a hospital, you should have different limits. I was going to harangue Dr. Nichols. Luckily, he left.
I'll let him know you're haranguing him. Don't worry.
Oh, no, I mean Jim. But John, why don't you put all this online? It'll be very sticky. People
That's a
from
great idea.
all your customers will get on, and all the other non-Bio-Rad people will be jealous, and you'll bring on more customers, okay? But this was really, really good. Thank you.
Thanks a lot, George.
Yeah, so I'll just have one comment. Yes, there are a lot of limitations to using biological variation for establishing allowable total error limits. And as you mentioned, just because something exceeds biological variation doesn't mean it's clinically significant. And that's why the EFLM, in their conference recommendations, did recommend that clinical outcomes be used as the preferred method for establishing allowable error limits. The problem is that we don't have a lot of data on clinical outcomes. In fact, I was trying to find this for an analyte the other day, and it was uric acid. And I really could not find that much data on clinical outcomes of different uric acid levels. Like, I was amazed. So I think that's why CLIA, in collaboration with the CDC, sort of defaulted to using biological variation for allowable total error. I did talk to Rex Assels, who did participate in that in the new CLIA PT limits, and he was stating that they did use biological variation in combination with assessments of current PT data and performance of labs, and figured out the state of the art performance data as well, and sort of used a combination of those two approaches for the new PT acceptability criteria. But yeah, there are limitations for each method of determining the allowable total error.
And George, just to address your comment, your suggestion, I think it's a very good one. We have some technology that is under development that, if it's of interest, please talk to your Bio-Rad representative, and you'll hear more about it later.
Hi, I am Yusuf Masamiri from Canada, Newfoundland. So I hear a lot of thank you for excellent presentation for the three. It's very, very important and very interesting. I want, in the agreement that we have in Canada, from Toronto, they obligated us to do now uncertainty of measurement. And uncertainty of measurement is 75% of total error. And we do that every 6 months, and it's a lot of work for us. But they want us to calculate only uncertainty of measurement, and we don't follow up what's happened after. So I ask my technician to be aware about peer group, about CV, decrease widest of CV and SD to be uncertainty of measurement. It will be good. Often we see total CO2, bilirubin is out, it's failed for uncertainty of measurement, because you know why. So I want to know what your opinion about uncertainty of measurement.
So my understanding of measurement uncertainty calculations, and I will confess I'm not an expert, so I may defer to John here, is that the calculations assume that the lab has removed the bias component, and that is a major limitation because, of course, we all know that we do have bias. And so if you're trying to use that to think about how you might perform with the new PT acceptability criteria, for example, it may not give you the whole picture.
I think that's absolutely right. I think there are tools that are out there that can help with computing the uncertainty of measurement. And certainly it is required for standards like ISO 15189 to compute that. So one of the approaches that's taken is having budgets, error budgets, around your uncertainty of measurement, like you just stated, of 75%. But I agree with Dr. Bachman that ignoring bias, I think, is kind of hard, particularly if you're looking at something like proficiency testing performance. You really can't ignore bias because it's a really big component of the overall scenario.
Bias is not really represented when you run a mixture of stuff that's not really a biologic matrix that you measure.
Yeah, but they are applying these criteria to the peer group programs, which may use non-commutable material, like you're saying, which is material that doesn't represent real patient samples for every assay.
And that's still the environment that we're living with.
Sorry, I have a question. What's the minimum number of users for if you're incorporating peer data?
Ooh, that's a great question. I think it's at 10. I can't remember if it's 10 or 9.
Yeah, it's 10.
It's 10, right? Yeah. So 10's the minimum. Hopefully, you've got a larger number than that, but 10 is the minimum.
Yeah, and if they don't reach 10, like if you're participating in the CAP survey and they don't reach 10, then CAP will switch to the all-method mean. So if your peer group has less than 10 participants, they'll switch to the all-method mean, or they may not grade it at all, and then you'll be having to establish your own grade for that result.
Thank you.
Yep.
Thank you. Just to add on that question, so if 10 is the minimum, is there any greater significance when we have more peers in the group? Let's say every incremental of another 5 or 10 increase what? I don't know. I mean, please elaborate.
Yeah, I think that, so earlier in Dr. Bachman's presentation, she noted that the guidance for setting your mean for a new QC target for a new control is 10 data points collected over 10 days. And the reason for that is that at 10, you've got a pretty decent estimation of the mean. I think once you get above, say, of course, it does depend a little bit on the imprecision of the test method that you're talking about. But I think in general, if you look at the difference between the means that are generated from 40 versus 100, they're very, very similar almost all the time. And so you really don't have to go too far, somewhere, after 20, that's a pretty decent peer group. But it does also matter a lot on how much variation there is and in the composition of the group that you're looking at. But I would say that anything over 20 is going to be a pretty decent peer group. What do you think?
I agree. Yeah. So I've seen studies, and I think the number is like 22, where basically you don't get any benefit from running more. And so that's where you'll see in a lot of the different guideline documents, 2022 is like optimal. It's the best use of resources without, doing overkill that doesn't really help you in the long run.
Hi, Dr. Bachman. Thanks so much for these amazing posters that I'm taking back to my lab. In your presentation, you had 12 patient sample comparisons. I was just curious if that was your standard or if that was just for the presentation.
Yeah, so we usually do usually our minimum is 10. If we have additional patient samples available, sometimes the techs will add on more. We do try to specify that they get a range of sample concentrations to span the range of the analytical measurement range of the assay. Sometimes that's not possible. So basically they're just selecting, so in that case, though, that was a subset of a greater, because it fit on the screen, that was a subset of many more patient samples. Because lipase is a very common assay for us, and when we have a QC failure, since we only run QC every 12 hours, I think we had many more patient results than that. I just couldn't fit them on the screen. So our approach is to repeat all patient samples between the point of the QC failure and the last good QC unless we have, more than a couple hundred. And if that's the case, then we go back and choose 10 samples every 50 or so that we can try to find the time point when the error condition occurred. And that kind of limits the sheer number of repeats that we have to perform. But if the number is large, if the error condition occurred right after the last good QC, and like one time that happened with calcium, we had 600 patient samples, and it was a clinically significant error, enough that providers would give calcium unnecessarily. And so we actually had to call in people to help with the repeating the patient samples and issuing the corrected reports. But yeah, we would do all of the patient sample, we would repeat all the patient samples from the time of the QC failure to the time when we could identify that the error condition occurred, if we could identify that time point.
So it's like you almost need a reverse QC procedure where you're looking for, when does this thing work?
Yeah.
This is true.
All right, let's give our speakers one more round of applause. Thank you everyone for attending. If you haven't had a chance, make sure you scan the QR code for your PACE credits. And if you want a unrolled version of the poster, we have those out front. So feel free to grab those on the way out. And thank you everyone for attending.